Hi, good morning. I just want to go through a couple of the homework questions that I've given so that we can have some clarity in this topic. The questions given were this 2013 question and this 2012 question. So firstly, the first part of this question says, define the term specific heat capacity. And we know the definition of specific heat capacity is the heat required to change the temperature of unit mass being 1 gram or 1 kilogram of a substance by 1 degree. To put this in the form of an equation, the equation for the specific heat capacity, C, is equal to EH, heat energy, is equal to EH divided by the product of the mass and the temperature change. Again, this is familiar to us. We should remember the equation EH is equal to MC delta theta. So that's the first part. The second part asks us to complete the table by inserting the correct symbols and SI units. In the first case, we have heat capacity. And we should know that heat capacity, capital C, is equal to EH, is the heat energy per unit temperature change, right? And if EH, the SI unit for EH would be, energy would be the joule, and for temperature change will be the Kelvin, all right? The SI unit of temperature is the Kelvin. Then the SI unit for heat capacity will be the joule per Kelvin. The second one is the latent heat of fusion. We said that the latent heat of fusion, LF, is the heat energy required to change the state of unit mass at constant temperature, all right? To change a solid, unit mass of a solid to a liquid without temperature change. And that's why the symbol for the latent heat of fusion is common L subscript F. Part three is something about gas laws. Write the formula for the general gas law, stating clearly each letter they represent. The general formula is P1 V1 over T1. That must be equal to P2 V2 over T2. P1 V1 over T1 represents the initial pressure, volume, and temperature. And P2 V2 over T2, they would represent the final pressure, volume, and temperature. I'm not going to write that down. We all know this symbolism. So you can write it another way. You can say P V over T is equal to a constant. All right? That if you were to multiply the pressure by the volume and divide it by the temperature of a gas, it will always be a constant. Of course, there's a condition for this. And what is the condition? The condition is that the mass of gas remains constant. And of course, that it remains a gas, right? When you cool some gases, you see they actually liquefy. So it must, this is only true if the substance remains. Actually, it's a gas law. So, I mean, obvious, that's kind of obvious. It must remain a gas. Part B, a physicist converts 8 kilograms of water at 33 degrees Celsius to steam at 100. Assuming no heat is lost, calculate the energy required to heat the water to 100. So what are we doing? We are taking 8 kilograms of water. We have 8 kilograms of water. And this water is at 33 degrees Celsius. And this part of the question is just asking us, how much heat would be needed to change that 8 kilogram of water to same 8 kilogram of water, still no change in state, at 100 degrees. And we see here that there's only a change in temperature. And when we did the equations, we said EH could go one out of two directions. EH could be MC delta theta or C delta theta, or EH could be M LF or M LV. And I tried to get you to understand that when there is no temperature change, when there is a state change, this is here you have a state change. When you have a state change, you will use this equation. And when you have a temperature change, we will use this equation, all right? So it's pretty simple. It's a map that I want to have you have in your heads. So in this context, this water is undergoing a temperature change, and therefore we have to use one of these equations. But because we were given the mass of the water, therefore you notice that this equation has mass. So this is the equation we will choose to work this part. It's simple thereafter. They're asking us how much heat was required. So EH would be the mass, which is 8 kilogram, multiplied. The specific heat capacity of water was given in the question to be 4,200, all right? So we can put the number here, 4,200. This is kilogram, and this is joule per kilogram, multiplied by the temperature change, which will be 100 minus 33. From this, we can crunch the numbers and we'll get our answer there. See. And I'm getting 2.25 by 10 to the 6 joule. I'll double check that. Seems to be correct. Next part. Second part of the question is how much heat is needed to convert the water to steam. Now, because we're now dealing with a change of state, we would clearly be using this form of the equation, mass by the latent heat of vaporization, because it is changing from water to steam at 100. So therefore, this EH for this part will be equal to M LV. The mass is 8 kilograms, and the latent heat of vaporization was given to be 2.3 by 10 to the 6. That is the 2,300,000, same number. And from here, we can run the calculation. And we will get 18.4 by 10 to the 6. 18.4 by 10 to the 6 joule. And the next part is asking us, what is the total energy in megajoule? I've already have the mega, we should know is 10 to the 6. That's what mega means. Required to heat 8 kilogram of water. This is a liquid. To steam, which is a gas. So we have to follow both of them. After we do this change, the second part of the question is doing this. It's taking that 8 kilogram and making it 8 kilogram of steam. Also at 100. So this required some energy that we calculated. EH, you can call it EH2. Right? and this one is EH. So what is the total energy needed to change 8 kilogram at 33 all the way down to 8 kilogram of steam at 100? And we simply have to add these two numbers. And when you add them, you will get 20.65 by 10 to the 6 joule. Remember, they want the answer in megajoule, so it's 20.65 megajoule. That's your answer here. So that question is done. Second question I'd given for homework was the 2012 question, which is again, state the general gas law. And again, we know that the general gas law says that P1 V1 over T1 is equal to P2 V2 over T2. And we can explain that. This part talks about a girl blew up a balloon. A girl blew up a balloon during the Christmas celebration. Explain in terms of the kinetic theory how the pressure is exerted by the air in the balloon. Now, by now we ought to know what the kinetic theory is. The kinetic theory really talks about the tiny particles that make up matter and uses the behavior of these tiny particles to explain the large scale behavior. All right? Uses the behavior of the atoms and molecules. Atoms and molecules are moving around very rapidly and bouncing into things. And when they bounce into things, they produce forces, all right? So what does the kinetic theory of matter say? First, the kinetic theory of matter says that matter, all matter, is made up of tiny particles called atoms and molecules. We're all familiar with that concept. But what the kinetic theory goes on to talk about is that these particles, these atoms and molecules, they're in constant state of motion. They're moving around all of the time. Now, in a gas, these molecules don't have any bonds. So in a gas in your room right now, you have molecules flying around, bouncing off walls, bouncing off people's forehead, bouncing off the light, bouncing off the mirror, traveling all over the room, colliding, all right? So the kinetic theory of matter says that matter is made up of these tiny particles, and these particles are in constant motion. When these molecules collide with objects, is like playing scooch. When these molecules collide with an object, a wall or whatever, the walls of the balloon, when they collide with an object, or in this case with the walls of the balloon, they would exert forces. That makes sense. If the molecules slam into the wall, they will rebound and they will exert a tiny, tiny force on the wall. There are many millions of molecules colliding per second. So the force produced is quite significant. So that's the first thing. The molecules are colliding with the walls, and the molecules are producing a force. Now these walls have an area, and we know the average of this force of molecular collision on unit area is what produces the pressure on the walls. So this is how, in terms of the kinetic theory, a pressure exerted by the air on the walls of the balloon. They're moving very rapidly. A molecule in a room, in your room right now, if you can guess, you can pause the video and think of a guess. How fast is the molecule moving in your room, a molecule of oxygen or nitrogen, how fast is it moving in your room right now? Pause the video now. Hopefully, you've made a guess. And typical speeds of molecules in a room is in the order of like 500 meters per second. Molecules are moving so fast. They're moving as fast as a commercial airliner. Really, really fast, much faster than the fastest human can run is about 10 meters per second. Even on steroids, you can only reach about 10 meters per second. But these molecules in the room, they're going at tremendous speeds, right? So we understand the idea of pressure exerted by the molecules in the gas. The second part of the question, part B, deals with a block of ice. A block of ice of mass 2,000 gram is heated. You notice it's gram. You have to be careful with units, right? Because when they give you gram, when we're dealing with melting, we want the latent heat of fusion to be in gram, but you notice it's in kilograms. So if it's 2,000 gram, keep remembering that we will have to ultimately convert this possibly to kilogram a little bit later. So you keep your eye on that. That's one mistake that students make. They mix up the units. You must match these units. A block of ice of mass 2,000 grams is heated from 0, so it's ice at 0, to steam at 100. Calculate the energy used in joule. Now, let's draw this block of ice. See, that's our block of ice. All right? And we're starting off as ice. But what happens to it as you supply heat to the ice? What's the first thing that happens to the ice? The first thing that happens to the ice when you supply heat to the ice is the ice starts to melt. When you supply heat to the ice, the first thing that happens to the ice is the ice melts. So this here would be liquid ice. The temperature would not change, the ice would melt. And if you supply heat to this is now water, it will produce water at 100. And if you keep providing heat to this water at 100, it becomes steam at 100. So let's write this down. Let's write down all of those things. So we start here with being ice, solid, at 0 degrees. And when you supply heat to it, this heat causes melting. So this is called melting. So it'll be absorbing a certain amount of heat to melt. I'll call this heat E1. Now we have, the ice has melted, so now we have a liquid. What is the temperature of the liquid? Still 0 degrees. The heat was only used to melt. If you keep supplying heat to this liquid, the next important point it will reach, it will remain a liquid, but it will remain a liquid up to 100 degrees, because remember, it boils, water boils at 100. This would absorb another amount of heat. Let's call that amount of heat E2. More heat. So we add this heat to melt, we add more heat. This is just changing the temperature. And then in the next state we're going, once you reach 100, you keep supplying heat, what happens to the liquid at 100? What happens to the liquid at 100 is boiling. Boiling. This is now a gas, having been boiled, but the temperature does not change. Boiling takes place at a constant temperature. This would absorb another quantity of heat, E3. Now the mass we had was 2,000 grams. So let's just call this, the mass of this ice is 2 kilograms. Let's convert it one time, 2 kilograms. Now, what is the equation for the melting? We ought to know that the equation for this melting is MLF. Because melting uses the latent heat of fusion. What equation would we use E2? E2 would be this heat E2 would be MC delta theta, would be MC, specific capacity of water now, by the temperature change. And the temperature change in this case would be 100 minus 0. Because the temperature is going from 0 to 100. And what is E3? In E3, we have boiling. Boiling uses the latent heat of vaporization. So this will be MLV. MLV. So to find the total, they wanted energy used to go from here all the way to here. How much energy is needed? To find that energy, that total energy, it would be equal to the sum E1 plus E2 plus E3. And let's put the numbers in. Remember, the mass is 2 kilograms. So this E1 would be 2 multiplied by the latent heat of fusion. We can get it down here. The latent heat of fusion is 330,000. Plus, so that's E1, plus E2 will be MC delta theta. M is again 2 kilograms. C is 4,200. And the temperature change, of course, 100 minus 0 is 100. Plus MLV. M again is the same 2 kilogram multiplied by the latent heat of vaporization. We see the latent heat of vaporization of steam is 2,250,000. 2,250,000. And when we run the math, we will get all of that. Okay, so I did a little speed up there. I did the calculation. So I wanted to record when I was punching in numbers. So this is what we get. That's the energy. That's the energy needed. E1 plus E2 plus E3. Again, this is the energy needed to take 2 kilograms of solid ice and convert it finally to 2 kilograms of steam at 100 degrees. The next part deals with the activity took 6,000 seconds. How much power is utilized? Well, what is power? That's the first thing we need to establish. I may not have told you what power is, but power is defined. Power is defined as the rate of change of energy. Rate of change or the supply, in this case, of energy. So like a 100-watt bulb, a 100-watt bulb, we've all heard about a 100-watt bulb and 60 watt. The watt is the unit of power. A 100-watt bulb means that it converts 100 watt, says that it converts 100 joule of energy every second, joule per second. That's what watt is. So that's power. Power is the rate of change of energy, how fast energy is changed. The equation for power, P, is equal to energy, of course, divided by time. That's what power is. Power is energy over time. And again, the unit of power is the SI unit of temperature is the watt, after an American physicist, James Watt. Now, we want to find power. That's the question here, P. Do we have energy? Yes, we do. The energy was 6 million. Do we have the denominator? The denominator is time. They told us 6,000 seconds. And therefore, how much power is utilized? When you do the calculation, you would get 1,000 watts. That is the power of the rate of supply of energy, or the power developed, or the power utilized, as the question says.